So welcome to the introduction to this course on autonomous robotics, action, perception, and cognition. So let me begin by talking just about what the word robot means or what people associate with robot. Last year, I did a Google search for the word robot in Google image. And the first page was this. Kind of interesting, right? They're all humanoids, all pretty much fake robots also that don't really work well. And then anthropomorphic robots. On page 2, there was a legged robot up here. There was a vehicle up here. And there was an industrial robot up here. Even some compliant, I'm not sure which page that was. So all of the others are humanoids. So regular industrial robotics on the first 4 pages were only this one here. Kind of interesting, right? Of course, in reality, industrial robots are really the robots that are deployed, and there are millions of them around the world. While all these humanoids are not deployed, they are all research objects or toys, and generally autonomous robots are not very strongly deployed. There are actually increasingly autonomous vehicles deployed, and I'll say something about that later. So this is just interesting about the perception. So perception of people is very much robots are anthropomorphic or humanoid robots, and that of course is the old myth. There's deep sources. I'm just writing a paper about that. Deep sources in mythology of the gods creating human-like machines and engaging them with giving them some kind of spirit and so on. It's an old idea. And so that is a very, very popular idea. And it's not entirely wrong, because I would say research, and we'll be talking about that, research in autonomous robotics is very much inspired by these myths, by these kind of ideas, creating human-like or animal-like organisms. Well, what robots actually technically still mean is really just programmable machines. So machines that are in some sense flexible, that have some kind of versatility. It's a form of automation that is flexible. So they can be quickly adjusted to different tasks. I will not really teaching about industrial robotics here at all. The emphasis, there will be a little bit about control, but there's a whole industry literally of software solutions for different aspects of industrial robotics, and that's not part of the course. So we're really talking about autonomous robots, of which humanoids are an example. I will not specifically talk about humanoids. I thought it was useful that I just flash a few pictures. You can see this, Google that yourself in a few minutes, but just give you a little bit of a flavor first of the sort of things we're talking about, what the hardware looks like, and by implication, what the use case is like. So the simplest are these autonomous vehicles. I actually own one of those vacuum cleaners, this little toy game where we're playing. We mostly use it as a toy. It doesn't clean that terribly well. These are deployed, as you know. There are a lot of industrial robots, commercial vacuum cleaners around now. Maybe I turn this off. It's a bit annoying. And these pictures are even a little bit dated now. You can go to Saturn and get the latest model. So that is practically some. They're typically robots that just cover ground, like a vacuum cleaner, and there are other cleaners or pool cleaner. They're not some of them purely mechanical, tennis ball collector and survey robots, mowers, and so on. So that has become mainstream. It's no longer a topic of research. Here's some of them. I will be showing. This one is like a Lego robot. It's not actually, it has only very few pieces of Lego, but it's the electronics that's inside the MIT. It was an MIT lab robot, but now it's a part of Lego's Mindstorm. The electronics of that is the Lego Mindstorm robot. This is a robot we built in Marseille, which I'll also be referring to, sort of a little bit larger than that, a little bit more capable. We actually built an autonomous wheelchair in Marseille, which did pretty well in corridor types of situations, even though it had very low-level sensors. So here in Bochum, we have stopped building robots ourselves. We were just using commercial robots. Outdoor vehicles. These are even older pictures. There's a lot of that. You famously have heard that there is autonomous robot on Mars. And then, of course, you know that autonomous driving is very much under research and advancing a lot. And these are, technically speaking, autonomous robots, right? There are really two classes of autonomous robots: arms and vehicles. And vehicles are actually much more advanced for reasons that make sense. I'll come to that later. The perceptual problems are simpler than those of arms that orient at objects. And so it's part of robotics. Legged robotics is an area of research. A lot of these are just from one lab. You've seen videos, I'm sure, of that. And humanoids would be part of the legged robots. It's a very interesting problem. Not always so clear it's really practical, but it's certainly interesting from a control engineering point of view. A lot of those are biologically inspired, so often inspired by the fact that animals don't have wheels, for also interesting reasons, and the the design ideas for such robots are often inspired by organisms. There are other sort of non-standard robots like crawlers and climbers and snakes, for instance, for inspection. There was a project here at Ruhr University in Maschinenbau, who were looking at pipe cleaning robots of that nature. You could say it's also somewhat biologically inspired because they're animals who move in that form. Underwater robots would be just autonomous ships or submarines. I mean, they're underwater or surface water vehicles. So that is actually relatively easy because the water is quite homogeneous, much easier to move in water. They have different problems. They have perception problems and they have communication problems because it's not so easy to communicate underwater. So often you have lifelines, for instance, to simplify that. And then there are vehicles. Somebody already mentioned a drone. Drones are now very attractive for this kind of research. Drones, usually drones are not autonomous, but when they are autonomous, that's an interesting platform. Again, their navigation is actually relatively simple in 3D homogeneous medium. It's just a question of control. And many of these don't actually do obstacle avoidance. So simple tasks are things like doing autonomous docking and autonomous avoidance of collision. There's a lot of military work on these sort of things. In drones and primarily in drones, big problem is the energy consumption. So the computation that is required in implementing some of the autonomous algorithms is quite heavy, and the drones are very short on energy. So there's a limit there. And actually, I'm involved in some work where we look at neuromorphic devices, so computing devices that already take neural ideas into account and are hoped to be much more energy efficient, even though it's still a struggle. Then hands manipulators are interesting. The industrial robots have grippers that are adapted to the sorts of objects they will interact with. And generally, interaction with objects is not a strong point of industrial robots. As soon as an industrial robot touches something with force being transmitted, there are problems. And it's a big topic of research how to do that. We humans have wonderful manipulable hands, flexible hands, and they're full of sensors. And we are very good in manipulating objects when we have a sense of touch. Maybe a few of you might have witnessed the absence. Even if you put on gloves, your manipulation skills are not anywhere near as good. Or like, for instance, if you have very cold hands and you manipulate something, then you might have noticed how clumsy you are then. And there are laboratory versions where you actually really anesthetize the hand and can then demonstrate that active sensing is very important for our manipulation skills. So there's a lot of work in doing that. We had a project with a hand that has a touch surface. I think I have here. This hand actually has a little touch surface here. And I like the sound a little lower. And it was supposed to help you with that perception. Frankly, it doesn't really work very well. It's still very, very primitive. So this is the arm that we're using still in our lab. It's a commercial arm, and that has a hand, the Coca hand. This is an older version. We still have the hardware, but it's no longer working. This is also a robot. We have a commercial one that has very limited manipulation skills. The combination of these two streams, the hands and the vehicles, would be arms mounted on vehicles, and there's a lot of work. This is some old photo, I don't remember. There's a lot of work on that as well. We had our own, we called it Arno, like Schwarzenegger, because it has this very heavy set, sorry. And it actually did one task very, very well, moving around rooms and grasping something, opening doors, but highly programmed. I'll come to some of those difficulties. So that's already a decade old or longer, 2 decades actually now. So that gives you a bit of a survey here. And I want to now talk a little bit about what autonomous really means, and that will give me an opportunity to explain better why vehicles are more advanced than robot arms. So autonomous, literally, it means giving, comes from autonomous. Nomos would be laws. It is giving oneself the laws and creating one's own laws of behavior. And so self means in practice that it's based on information that the system itself acquires about the environment in which it acts. So typically would be onboard sensors. Maybe the sensors could be, doesn't always have to be physically on the body, but would be accessed by that system. It would not be pre-processed with the help of outside systems. For instance, an industrial robot would have a complete plan of where everything is on that table that's provided to the robot, and there's a fixed action plan that would act on that information. And so everything in that sense is pre-programmed. It's flexible in that you can reprogram it, but it is not flexible in the sense that it would itself acquire the information that is required to act, and therefore it wouldn't reprogram itself. It would have to be reprogrammed for a new task. So that's roughly autonomy. And so I'll come back to this question of vehicles in a moment. So, this sounds maybe clearer. If you look a little bit more closely, then you recognize, of course, that all robots are controlled. Engineers will know what I mean by control. So they actually all have some form of feedback control. There is some sensor that informs about the state of the robot and that corrects the state of the robot. So for instance, minimally industrial robot will have some form of servoing that is estimating the pose of a joint, of a robotic joint, and then sending currents to the motors there to make sure that that joint has, for instance, a desired joint velocity or has a desired position. Such control is also called autonomous control because you have a sensor to control. We wouldn't call that really robotics in the sense of autonomous robotics, in that it is really very limited. It's just given set value and you realize just that one set value. Well, in robotics, we expect something more complex to happen, more than just controlling for one particular value. To make that precise isn't quite so easy. One can think about decisions being decisive, that you bring about some decision, you make up your mind, for instance, you go around an obstacle on the left or on the right. Now, that will be something that is more than control. It is making a decision. Like if you reach for an object, maybe if you have multiple objects and you select one, you could say, well, that is a decision, and that's not just control. It's not entirely clear how easy that is. For instance, some of you might know that optimal control, in a sense, generates an appropriate motor command to achieve a goal, and then it's more than just one value. It's an entire trajectory that's generated. So where the exact boundary is not so clear, but it's certainly autonomous robotics is meant to go beyond control, beyond autonomous control. That's what traditionally is the motion planning part there, where the complexity comes in. In these neurally inspired robotics, it's not so clear if planning and control are really different. So that's technically what autonomy is. Sometimes people also think autonomous means that the robots does what it wants, right? It has some program according to which it would decide, for instance, to go back to home base to charge and to maybe to explore the environment, to improve its map, and so on. And some algorithms are like that. That is actually also not entirely what we want. There is always often a idea that there would be some kind of limitation on how autonomous the robot can be, which is that we want it to fulfill certain tasks, which really means we want to give orders to the robot. And maybe the one reason why we want to have a robot rather than, let's say, train our dog is that we hope that we would be able to give orders to the robot very easily, while it takes forever to train your dog, and certain things it would never be willing or able to do. So here's an example, again, sounds really high here. It's a robot we built that has speech interface and some gesture recognition. Stanis Josefidis, who did this, would now teach us in Bottrop at the Hochschule Bottrop. And you see he was pointing at an object and the robot then grasped that object. And so that's a view of autonomy where you would say, well, I can give orders to the robot, but I can do it at a relatively high level. Here in this idea, this demo, it was the idea you can give it at the level of language and gesture and so on. So it's not programming, even though technically speaking, you're setting goals for the robot by that interface. And so the autonomy then consists of the robot dealing with the details of that. That is figuring out in each case what specific movement it needs to make, and what part of the perceptual array to analyze and extract the pose information about the object from, and so on. So that's probably the most reasonable narrowing in of the concept of autonomous. There is some degree of autonomy at the low level, but there would be a goal setting that comes from a interface to a human user, or something that's programmed again. For instance, maybe a military robot you would program to shoot down enemy planes, let's say, and so you're only giving autonomy within that global task. Good. So why would we want to do that, right? Why build autonomous robots? I've actually asked a lot of people, including my son, and sometimes people say, "Oh, like really cool, do something cool, like serve drinks or clean up my kitchen and so on." Robot soldiers come to mind very easily. That's sort of analogous to this thing when you Google robotics. It's always these humanoid robots. So one can be a bit skeptical about whether these are good reasons. It's only very far from reality. Actually, in the autonomous robots that are deployed are often purpose-free. A lot of them are just toys or for fun. They're also very limited in what they can do. There is some serious effort in making robots part of therapy. There's a lot of work on autism. Somehow autistic, we're talking about somewhat severely autistic people, sometimes have less trouble interacting with a robot than with a human for some reason that people now study. It's a very special case. So there is that sort of domain where it's not achieving very specific goals. It's really just some interesting interactive thing. The goal of a lot of work where that would be the first stage would be to have a real assistance systems. So that's the official thing. It's actually interesting. In the European Union very much funds assistance systems. It's all based on improving life for humans. It's very much this humanitarian European perspective. And for instance, the US is very much more interested in military robots. And interesting, the Japanese and Koreans are very much interested in toy robots. So interesting cultural biases. So we Europeans, it's always about being the good guys, morally, and helping. So that's a research program. I would say actual human assistance robots are all in the lab. There is no real working system at the moment. Certainly not when it's mechanical. There's some dialogue systems, but not when it's anything where it's an actual actuator and does something. Autonomous vehicles, by contrast, are already somewhat common. Unfortunately, I show here the Amazon warehouse because it's very impressive. It's actually, they have the largest deployed number of autonomous vehicles in the world. It's not very autonomous, actually, so it's very much centrally controlled. The autonomy is really just that they stop if something is blocking their way, and they send back a signal that they have stopped. But but it's very developed, as I mentioned earlier, autonomous driving and in all kinds of, sorry, actually, I don't have the right picture for this. Autonomous driving is much easier than object-oriented action because perception is much simpler. And you can actually see that in the animal kingdom. If you think of animals, then almost all animals achieve almost everything they do like a vehicle, I mean, with their body. And what that means is that it is a situation in which the sensor moves with the body. So for instance, if you walk around, your eyes are carried through the world, and therefore the eyes, the sensory information in the eyes depends on the action. So they're immediately part of a closed loop. So for instance, when you walk, then there will be an optic flow on your retina that goes backwards, and that informs you about how fast you walk. Or if you stand, it informs you about whether you're falling forwards or you're falling backwards. And that enables strategies where you can use sensory information in a fairly global way. You can just average the visual velocity on the visual array to have an estimate of your ego motion. There's some work on that without having to distinguish between different objects in the world and distances and things like that. And as a result, dealing with sensory information, actually also using relatively low-level sensor information, just some distance measurements, and I'll be lecturing about that in the first few lectures about vehicle motion planning, where it's enough to have just a few distance measurements, and you're able to avoid obstacles and move around the world and reach targets without ever having perceived an object and sort of delineated the object from the background and organized your action toward that object. So the perception side is much easier, or I mean, the relevant part of the perception side is easier for vehicles. That's one reason why vehicle research is really much more advanced than autonomous grasping and manipulation and things like that. There's another reason is really, I'll come to that, is the manipulation of surfaces. So contact on surfaces is really difficult. Now, the other use of autonomous robotics is military. We don't learn so much about that because there is a lot of work. It's often confidential. It's an ideal application from a technical point of view because it makes sense to take humans out of the equation when you're trying to kill each other. And it's difficult to do all of that with remote control under relevant circumstances. So that's very attractive. There's a lot of work on it. A lot of people don't find it ethically okay to do that research. You can have different views on that. The milder European version of that would be catastrophe firefighting rescue robots, but they have, because very special applications, not such a broad application scenario, but there is some work on that, and it's not very advanced actually. There are interesting issues about ethics here, by the way, and they don't show up only in the military robots, where you want to maybe have a human in the loop for deciding something lethal. It's actually been practiced for a long time that under certain circumstances, ships would automatically fire at incoming rockets. So it doesn't have to be really modern robotics to do that. There's also a lot of discussion about that in autonomous cars, if you have avoidance strategies, to which extent do you protect the passenger of the car versus the pedestrian, and what kind of trade-offs can the algorithm do, and so on. So interesting stuff. It's still a bit premature because they're not deployed, but in autonomous cars, it becomes relevant soon. Now, the true reason, I believe, why many of us actually do this research is that it is a very nice research platform. It's a wonderful playground for research. And I'm going to give you 3 arguments why that is the case, or 3 concrete forms that takes. So this is a little video from something we did, and this demo actually is about online updating, where the object is shifted after the robot has begun to move. And the special research question here is that all this movement here, even though it looks a bit jerky, is actually, now the movie is running backwards, is actually one dynamical system unfolding in time. There is no algorithm here other than the numerical solution of the equation. So that's, it's clearly a research demonstration. It's not about this being a practical skill. Now, so why is it an interesting research platform? So one global way to talk about that is to say a lot of modern engineering is based on a core idea, which is that you model systems very well, and then you can predict everything about them except for some noisiness, stochastic, which you treat by stochastic models, and combining that, the stochastic models with the prediction, you control these systems very well. There's a lot of theory about that, Kalman filters, optimal control, and with that, we've been able to solve a lot of problems. Some of you might know that initially it was very hard to control rockets because rockets, for instance, change their inertia very drastically. Initially full of fuel, then a little later they're empty. So the same kind of control signal will be too weak when they're full, and then too strong when they're empty. And then there's very clean theory developed about how to do that optimally today. And all of that is very successful. And so you could say autonomous robotics is exactly pushing the limits on that, because in autonomous robotics, you want to have them act in what we call natural environments, that is, environments that are difficult to model. That's what it actually means. Natural environment means just we don't have a good model of it. So the industrial robot would be the extreme, where you have, let's say, a CAD model of the product that you're working on and of the work environment. Everything is pre-coded, and there you can very well work with classical robotics. And then as you introduce more and more uncertainty and maybe even categorical errors, that there are objects out there for which you don't even have a model, you have to develop new techniques how to deal with them. That's very interesting. So that's driven a lot of research in that domain. So for instance, the particle filters would be an example for those who know these sort of things. And a lot of learning techniques are about that. Learning techniques in neural networks would be about acquiring information about an environment that you have not yet modeled. By acquiring that information from experience, you hope to automatically develop the model. So that's sort of a principal reason why that's an interesting research field. A related, slightly different reason, though, is that that modern engineering is also using modular design a lot. So modular design means that you have components you design, and you limit the range over which these components influence each other. And therefore, you're making it possible to design these components independently of each other, for instance, by different teams in a big project. And they just provide specifications to each other, which are the interfaces, and then they can do their work independently. And what, yes, is there a question? Oh. So they do their work independently, and they can then assemble their modules into the working system, and by being consistent with the interfaces they defined, they can be sure that the whole thing works. Very similar ideas used in cognitive science, in cognition, the old idea of the modularity of the mind. Jerry Fodor was a famous proponent of that idea. It's a component that the mind consists of modules that have a certain information processing function, and by defining that function, these modules are defined, and how they achieve that function inside doesn't matter. And therefore, the function of a module does not depend on what happens elsewhere, only to the extent to which their input is modified. And that certainly makes design possible, makes it possible to scale and so on. And so autonomous robots are interesting challenges for that. And you can try to build them this way. There are some well-known demonstrations of limits of that. I'll give you maybe an intuitive picture for that. For instance, if you have a road following algorithm that makes sure you stay on the road, and you have an obstacle avoidance mechanism that makes sure that you go around an obstacle, you can see there can be a conflict, because if the obstacle avoidance tells you the best would be to go around the left, but the road following says you want to stay on the right, you have to integrate these two in some way, right? So you can't actually separately solve these tasks. There are a lot of examples like that where the behavioral analysis actually makes it a challenge to integrate the constraints at the same time. We'll be seeing a little bit of that in the first couple of lectures. When I'm talking about path planning of vehicles, it's actually about multi-constraint satisfaction, which is exactly a problem of that nature. So that's the second area where this is an interesting topic. A third is just the interdisciplinary nature of it. That's maybe less research, and also in terms of training and application. For instance, a lot of student projects are around robotics and often attract students. And part of the fascination is that when you build a robot, well, maybe a drone, as one of you mentioned, and want to program it, you have to deal with all the different components. You have hardware, you have mechanical hardware, maybe you have sensor and electronic hardware. You need to wire up that hardware so that they all communicate with each other. You need to have a programming interface for that. You probably need some embedded computing to do anything reasonable. And more globally, you have control, AI, planning, and perception. These three, perception, control, and planning, or artificial intelligence, are the more typical autonomous robotics kind of problems, which you always, they depend on each other. Depends on what perception means. What information about the world did you extract from your sensors? And so that will be your world model. And what you plan can depend on what you have available from perception about the world. And when you plan something, you have to take into account whether you can actually control that, and you can actually achieve that with your plan. There might be some constraints from achievement that you already want to put into your plan. For instance, limits on acceleration or on maximal forces you could generate and so on. And so that's quite a large range of subdisciplines. I think communication, where I mentioned data security, it's a whole different area than, say, the mechanical engineering, even control engineering. User interfaces, how you program those, it's different discipline. So a lot of different fields are connected when you're building autonomous robots. So that's an interesting challenge. So a few words about where this field stands. It is currently going through a rapid expansion. There have been different phases. It's been also stagnant for a long time. Initially, the 50s, there were some first demonstrations, and then a long time, nothing really happened. And one revolution was when people went actually away from this picture and found much more simplified cases, not having a general model from which planning was derived, but had sort of ad hoc simple behaviors. Some of the progress just comes from scaling, from having better computation, more massive computation, and being able to use higher dimension sensory input like vision. And with some theoretical breakthroughs, the probabilistic approaches, which I will not be teaching here, unfortunately, it's much more technical. The probabilistic approaches have made it possible to use sensors like laser rangefinders, would be sort of the ideal sensor for that, or other sensors that are just distance sensors that were in some sense much lower level, simpler than, for instance, vision sensors, and that were still enabling systems to extract relevant information about the environment. So that made a big breakthrough in autonomous driving. Today, it's also software engineering helps. There's much the programming, very typically to have a robot do one task autonomously was one doctoral thesis, like pick up a spoon, and then the next task was another doctoral thesis. And there's been a lot of progress that more components that can be more easily be reused, partly just because of engineering progress, partly also because there's some principles. I will be talking about one principle, the so-called motion primitives. That is a way of making in a way the programming of behaviors more modular. So generally, there's much maturation. It's not one specific breakthrough that is driving that field forward. I want to talk about areas that are not working so well, or that are the main challenges. And only I will be largely only really talking about the movement generation problem in this course. I'm talking about the first two problems in the winter semester course, not talking much about the background knowledge problem. So start with perception. So perception is not just working on the stimulus. It's not estimating the stimulus. It's about extracting what it means. That is, extracting information about the world that caused that stimulus to arise. It's very clear in vision. In vision, you have some image, right? And image processing would be filtering that, or enhancing contrast, or all kinds of things. But what we mean by computer vision is that we find out about the world, the 3D world and its properties, from the image or from a video. For instance, you might be attentionally attracted here to this arm, and selecting that arm as the center of your attention is one of achievement. Maybe you have a task like, where's the robot, or which brand robot is in that picture, and then you have to find where the robot is, and you have to recognize it as a robot, and you have to focus on that robot. And maybe when the view changes, you might have to recognize that it's the same robot from a different view. So these the four categorical problems in perception are this form of attentional control that's not very well dealt with so far, classification or recognition, which is actually currently being, there's a lot of work that improves that a lot, sometimes to superhuman performance. Segmentation, knowing precisely where the boundaries of an object are in the image, maybe also in a world model, and then estimating, like estimating the pose, orientation, or certain other parameter values. Those are all problems that are important in perception, and you see they are particularly important when you want to estimate properties of objects that you want to direct your action at. That's why reaching and grasping is challenging. When you do control of a vehicle, you often don't need attentional control. You might need some classification, like traffic signs and little things like that, but not for a lot of tasks. You very often don't need real segmentation, and estimations often just limited to estimating your pose, like in a map, or your pose on the road, and so on. In the winter semester, I'm teaching about some aspects of that, but with a much more strong neural perspective than I'm mentioning now. Yeah, let's skip that. The interaction with humans is also a very active research field. So this would be that programming interface, how to talk to robots. And I feel that hasn't made that terribly much progress. So I was sort of seeing very similar ideas for many years. So in a sense, you could think it's part of the perception problem, because you have to perceive the user more precisely. You have to perceive the user's intention. That is actually really more difficult. We humans also struggle to figure out what someone wants. So one instance of that is to perceptually ground language, right? You can have a language system that parses the words and maybe finds out the syntax tree. For instance, there are programs that are not terribly good, but that can type, write in what you dictate, can take dictation. Have recently become much better than they were for a very long time. But that actually is not yet grounding, because that doesn't mean that that program knows what you're talking about, right? To know what you're talking about means that you have the robot has a perception system and is able then to do these perceptual tasks, the attention selection, maybe the classification, maybe some estimation about the objects from what you said. For instance, if I said the red cup to the left of the green cup, you can figure out it's this one here. It's not that one. This is a particularly tricky example, right? Because there are two green cups and there's nothing to the left of this green cup. So it must be that green cup that one is talking about, because there is something red to the left of it, right? This is already problem solved. It's a real cognitive operation where to ground that language, to know which cup the speaker is talking about, you have to go through different hypotheses and reject some and then accept others and so on. So that is an area of research. Some applied research, just these very practical aspects of it, but it actually goes deep into cognitive science, into understanding what it actually means to ground language. Imagine a robot that can ask questions back. That would be a robot that's able to, what we call framing, to frame, is to know what to talk about and what reference to take and so on. More practical things like gesture recognition, dialogue management. Emotion recognition is a field of research, even though it's a bit debated sometimes about how solid it is. I'm lecturing about parts of this, again, from a strongly neural perspective in the winter semester course, and you've seen that. It's not very applied, it's not really in a robotic interface sense. It's much more basic research. Then background knowledge, I changed the order here in these slides. I just want to make you aware that that's the old AI problem, right? It's the problem about knowledge. And so in AI was this knowledge, like experts, so find out about medical concepts or stock market concept. So you have a system that can autonomously, answer patient questions or can speculate at the stock exchange. In robotics, it's much more down to earth knowledge about how the world works, and that's actually even harder because a lot of that is very implicit. We humans are not actually very aware of it. How do you open a door? Where do you find milk? How to grasp a glass or a spoon or a cup or an egg? Different constraints there. How to grasp something in order to then do something versus something else. If you want to move something, that you first want to clear out the space where you move it, very trivial things. So that's something you have to tell every autonomous robot in every situation. Is very little theory of what that knowledge would be, the mechanical knowledge of the world or the actional knowledge of the world. So very difficult. So that's the old problem of how to get that kind of knowledge into an artificial cognitive system, into an autonomous robot, how to maybe autonomously get that. So how does the robot learn from experience itself all the time, as we do? When we build the second copy of an IKEA piece of furniture, we do it very well. The first time we make some mistakes, and then the second time works very well. That is a major challenge, to get robots to be able to pick up knowledge that way. So I'll not be talking much about it. Just mention it's a classical problem. Some knowledge in the nervous system isn't actually information. It's not stored somewhere as information. It is in the skills. It is that you are adapted to your environment and you have certain ways of doing things, moving and interacting. You built also in a certain way that solves some problems. So for instance, we as humans are characterized as robots, as movers, by our compliance. So we can apply variable amounts of pressure onto an object. Actually, when I make this kind of movement here, up and down, lift my phone up and down, then I will actually, without any conscious thought, I will modulate my pressure. Now, how strongly I press here on the sides on the phone with the phase in the movement, anticipating the fact that when I'm at the acceleration point, when I turn the trajectory around, there will be increased force that imposes the risk of slip, and to prevent that slip, I will press harder, and that is sort of built into my periphery as a behavioral pattern that's automatic. And in a sense, that's some kind of knowledge, knowledge about the kind of things that can happen. It's not like you have to say, oh, when I accelerate an object, I better grasp it hard because it could slip. It's part of your behavioral organization. There was an approach that was called behavior-based robotics. It's still being used. Some portions were still being used that attempted that. That is, that said, well, let's build elementary behaviors, and each behavior has its own sensory motor mapping, and those capture some knowledge about how things work, rather than represent that knowledge in some database that we look up. So I'll be referring to that a little bit. The way I will be referring to it, it will all be built by hand, by copying from the nervous system. Will not be autonomously acquired. And the last problem I want to talk about is really movement generation. So how you actually move, right? How do you do that? Now, that's something that where there's an interesting contradictory situation. So on the one hand, modern robots are extremely good. So first of all, industrial robots are very good. They have very precise, high replicability from movement to movement, superhuman performance in that way. Very fast. They can move enormous forces when loads when needed. They can be scaled to do that. And they actually do that with relatively simple methods of control, I should say, the deployed industrial robots. But it's also possible that actually the research on that is very advanced, to have very sophisticated robots that then do this optimally. A famous example are these robot arms mounted on spaceships, like the space shuttle had an arm like that, and there's one on the space station. That's relevant because if you're on a spaceship and you move your arm just in some brute force fashion, the whole spaceship, there's no earth that is connected to that arm where the momentum could flow, or the angular momentum you're generating, it's conserved. So the axial reactor, the opposing angular momentum has to go somewhere. In the Earth, it goes into the Earth. But if you're on a spaceship, then the whole spaceship wobbles, and so you have to make sure you make movement that minimizes the changes in force, or the changes in linear or angular momentum. And there are really good methods for doing that. They're based on having very good models of the arm, and the hardware is very suited to implementing these models. It used to be a computation problem, which is no longer is. So in that sense, it's very good. The classical approach is really very sophisticated, both in this brute force and the sophisticated way. But on the other hand, where it's not very good is when it interacts with the world, and that world is not perfectly modeled. So first of all, it has a hard time really dealing well with the world just whose mechanical properties are known, or you don't know the weight and things like that, and when you don't know the surface. And so as you touch it, you might encounter the object at other positions than maybe predicted, and then you have to react to that. So you will find that, for instance, when you take a modern robot arm and try to make it have a mechanical effect on an object, like what is called fräsen in German, which the English term approach I just forgot, where you take off a little bit of material with a tool, that turns out to be quite difficult with robots to do that stably without creating some kind of oscillatory reaction. And that is not just by chance. There's some deeper problem behind that. Now, that is something that we do very well as humans. We can polish a car with different kind of surface. We can apply different amounts of force as we do that. When the piece of cloth that we use is more sticky or less sticky, we can easily adjust to that. We get better as we do that. So we're very good with soft actuations, safe interfacing with surfaces. And part of the reason is that we're relatively weak. That is, the total amount of force we can generate is not so high compared to the kinds of loads we can lift and precisely. I mean, I can take a 20 kilo weight and position it quite precisely and softly on a table surface, for instance. On the first trial, the first time I ever lifted that. And when I do this in class, I actually demonstrate my strength by lifting a chair with one hand and positioning it very well on the tip, let's say. So that is interesting, that we can do that, even though we're not as strong as a robot arm is. A robot arm will be able to compensate for any kind of disturbance by generating opposing forces, and that's certainly not how we do it. That prevents us from injuring ourselves, so we will not easily break our own bones by applying unreasonable amounts of force to the surface. You can actually push the limits on that, but our typical movements will not be so forceful as to hurt ourselves. So we're using actually also the viscoelastic properties of our muscles and tendons to create that kind of compliance and softness. But we can also control that compliance and softness. So when you work on an object and you put in your one hand and then you work with the other on it, then that is then you're actually in a very skillful way stabilize this object just right, so that you can transfer the right amount of force. So that's something where we are unmatched by technical systems. There are actually a few robotic applications where a human is the compliant part, wiggles in the last few centimeters. A famous example was the satellite capture, when the robot arm on the shuttle was developed to capture satellites, where after a lot of problems, the solution was to strap an astronaut to the end of the robot arm and have the astronaut catch the satellite and then wiggle it into the mechanism, because the human is so good at that compliant action. So they were very good. What that then opens up as the question is, how do we actually then do something precise and fast, which we can also do, right? We can hit a tennis ball with high precision after some practice. And so with very high speed. Because if you have a very soft arm like that, then it doesn't necessarily follow your command so well, because the moment you send the command and the moment when there's a big delay between that and then the moment when the arm actually accelerates. So how do you do that? That's a field of research. So I will be talking about that a little bit, not in terrible depth as you can imagine, but I will give you some ideas about that toward the end of the course. That will be a topic where we'll be exploiting that analogy between human movements and the robotic movement problem. Okay. So that's sort of the survey over the fields. I want to last point out that this course takes a really particular perspective on this field. This is a very multifaceted field. And I'm taking this particular perspective of autonomous robotics as a research field, first of all, not as an applied field. I'll not really talk about technologies that are deployed or that current benchmark systems, not. And I'll talk about it as a research field that is a partner for a theory of cognitive systems, where I come from. Autonomous cognitive systems is sort of the sophisticated word for autonomous robots. Technically, an autonomous cognitive system doesn't necessarily have to have an actuator. It could be just a dialogue system or something that just talks about stuff. But it's very natural to also think of it having some aspect of actuation. And so the autonomous robot is like a model system for that. And so it's an example of such systems. And so part of our research is really about finding out about principal problems. There are principles in the sense of, the fundamental that to develop a theory of these problems, analyze them, and not just find ad hoc solutions to all of them. And typically in the interdisciplinary spectrum that I just hinted at, the different subproblems will be dealt with in different theoretical frameworks. For instance, planning will be algorithmic, perhaps, or some form of optimization, and then control will be optimization and dynamical systems, and communication will be in information processing terms, and perception will be, again, in terms of feed-forward mappings, and so on. They're very different kind of languages. And so what we're interested in is to find formulations for these problems that lend themselves to integration into a behaving system. And we propose specifically the language of dynamical systems as such an integrative framework. And that actually is the language that we're also proposing as being the language of how we can understand the neural basis for cognition and behavior. So what we also do is we use the robots as tools to test such models and behavior. That's in our research. And in the course that will show up a little bit. I will not talk about it very strongly, but occasionally I will refer to insights from the robotic demonstrations for theories of cognition. So for instance, when you build a robotic version of a model of, let's say, human cognition or human movement generation, it can often be very interesting because it can help you, first of all, prove that your model is good enough to actually bring about that behavior in a technical system, in an action mechanical system. That shows some kind of feasibility. And also, it's actually often interesting in uncovering problems that have been overlooked. The most overlooked problem in a lot of models of neural function is calibration, of how to actually get internal states to really stay in correspondence with something physical, for which you need some kind of alignment procedure. And that is something that is typically solved by some form of adaptation. And when you do that on a robot, first thing you find out is you have to figure out the coordinate frames in which everything is defined and how they relate to each other. That makes you very aware of these kind of problems. So in the course, the first will be the most visible part. And so dynamical system, that I'll give a tutorial about that next week, takes the form here of what we then will call behavioral dynamics, which is more what control theory is about. as contrasted to neurodynamics would be the inner state of the nervous system, which is really the topic of the winter semester course. I will be touching on some aspects of that. Those who have listened to me in the winter semester know that we're mainly talk about population code or space code, where peaks of activation over some space represent states. Here I will be sometimes talking about the rate code picture, where activation itself evolves in time. For instance, when you make a movement and activation goes up and down as your muscles contract or not. So I will be using neurodynamics only in that more special sense. Other than that, it would be largely behavioral dynamics. So this course is not just a standard introduction into autonomous robotics and technical introduction. So if you take a textbook of robotics, there will be some overlap, like the path planning will be a little bit like that. I will be having a short introduction into some kinematics, but it also has about half of what we do in the course is not standard autonomous robotics. So it's not intended to be a course for a curriculum in autonomous robotics, like maybe the Dortmund program. This is somewhat unorthodox, an unorthodox perspective that is really driven by this analogy to the nervous system. So here's a syllabus, a survey over the contents of the course. I will begin next week by giving a brief dynamical systems tutorial. Some of you might have heard parts of that in the winter semester. It overlaps with that. That's sort of to get you up to speed. It's often something where the first couple slides, you will think that's very well known if you're an engineer or physicist, but you will see actually it goes a bit to the limits of your knowledge. I will end up on bifurcations, for instance, bifurcation theory and things like that. And then we will actually use these concepts right in the first approach to vehicle path planning, which is the attractor dynamics approach, which I myself developed. I'll also give a survey over some other approaches and compare. There will be an interesting comparison to what's called the potential field approach. And I will also give some link to more recent approaches, like the dynamic window approach. And that will be sort of one block. It takes about like 4 or 5 lectures, I remember, maybe 4 lectures. It actually different levels of a attractor dynamics approach. And I'll show you some hardware implementations. I'll also show you how these approaches model human behavior. When humans locomote, their path in the plane is sort of like a vehicle path. How do you walk as a pedestrian? And it's not about the leg falling, but about the body in space. And actually, some of these models have been used to model human pedestrian behavior. And I'll show you some of that. So that's one module. And then the second half, it will be a little bit more than half, 60% or so will be about robot arms, the 2 systems I'm talking about, the robot arms. So we'll have a little introduction where I just tell you about the kinematics of robot arms and dynamics, inverse kinematics. And this is what is, if you take a regular course in robotics, that will be a large part of it. I will just do that in one double hour. So it will be quite compressed and just more conceptual. I will then actually talk about movement generation in a much more biologically inspired way, talk about coordination, timing, the generation of time courses, movement primitives. I'll hint at a neural architecture movement of what we know about how the brain generates such time courses. And then there will be a chapter about motor control. Motor control really means how you physically bring about the movement with actuators. And that includes controlling them, that is updating their commands based on the outcome. So I'll have a quick lecture on the technical way of how control is viewed for arms, like inverse dynamics and computed torque, so on. But that will all be also, that's something that in a regular robotics course would take a major emphasis, and I would be compressing that quite strongly. And then we'll talk about human motor control. We know about it and about muscles, the dynamics of muscles. They don't generate force instantaneously or not very fast. It's actually quite noticeably delayed over the motor commands, and reflexes contribute. The reflexes are active during the movement, and they actually sometimes oppose movement. You have to understand how that is taken into account. And that's will be the end point of the course. That will be going back really to biological movement or movement generated by organisms.